Hello, this time around, we're going to take a look at quadratic functions and some of their properties. So in our last video, we took a look at linear functions and how to model things with linear functions. And as we mentioned then, linear functions are first degree polynomial functions. So it only makes sense that we should now take a look at second degree polynomial functions. So polynomial functions of one variable, typically x is what we like to use, but doesn't have to be. And the highest valued exponent on the variable will be 2. So we'll have an x squared term instead of just an x to the first term. So you guys have studied these a little bit briefly in Algebra 2. We're going to take a little bit closer look at them this time around. So without further ado, let's define a quadratic function. So a quadratic function is any function that can be written as f of x equals ax squared plus bx plus c, where a cannot be 0, because if a was 0, we wouldn't have an x squared term, so then we'd have a linear function. So we don't want that. We want that front number to not be 0, so not to be 0, and a, b, and c are all going to be real numbers. So our variables are x and f of x, or y, right? Remember, f of x is another way to say y, but it's function notation. It's just letting the audience know that what follows is a function of x. So a little bit of vocab here, a little bit of vocab. This is called the quadratic term. Because it's the term that decides, it's basically the deciding term that is how we know this is a quadratic function. So by having that term, we have a quadratic function. Whereas this is the linear term, right? Because we have x to the first power, so that's a linear term. And then this right here is just our constant. So a quadratic function is made up of a quadratic term, a linear term, and a constant, all being added together or subtracted. But remember, subtraction is technically defined as the addition of the opposite. So it's basically a trinomial whose independent variable's highest exponent, valued exponent, is 2. And it's got to be an integer exponent. All right, so if we can write our function like that, then we have what's called a quadratic function. A couple important pieces here. The domain, right? Anytime we have a new function, we should know what the domain is, what values of x will return a real value back out for y. So if you look at the function, all you're doing is squaring x, multiplying it by a, multiplying x by b, and then adding some real numbers together. So nothing in there is going to prevent us from getting a real value back out. Every single number you plug in for x, you're allowed to square it. You can square any real number. You can multiply any real number by another real number, and you can add any two real numbers together. So there's no arithmetic in this function that when you try to do it will not return back a real number. So the domain is all real numbers. You can plug any value you want in, any real number you want for x, and you will get a real value for y back out. Well, as we're going to see, by having the x squared term, the average rate of change will not be constant. This graph will not have a constant rate of change. The slope will not be the same everywhere on the graph. So it must be something else. So this graph is nonlinear. This graph is nonlinear. And as you may remember from Algebra 2, it's actually parabolic. So the domain's going to be all real numbers. You can plug any real number you want in for x. Nothing's preventing us from doing that. And then it's nonlinear, though, because the average rate of change will not be the same, as you will see. And then its graph is actually what's called a parabola. So again, remember, this is review from Algebra 2. So we're not going too deep into this. We're kind of hoping by just going through it briefly, we kind of want to focus on the bigger picture here, that we've studied first degree polynomials. Now we're going to study second degree polynomials. And then what we really want to do, what's the important part here, is here pretty soon we're going to talk about all the rest of polynomials, kind of look at polynomials in general and start to understand them as their own entity instead of like the specific degrees. All right, so the graph of a quadratic function. Well, it's a parabola. So as you may remember, a parabola. Now remember, we're doing functions. These are functions of x, so they're going to pass the vertical line test. So if they're going to pass the vertical line test, then the parabola can open upward. That's a possibility. So this could be our quadratic function f of x. It would pass the vertical line test. They are symmetric. They are symmetric about this line right here that passes through this important point down here at the bottom. So we call this the axis. We call that the axis. And this important point down here at the bottom, right here, we call that the vertex. The vertex is the point at which the graph changes from decreasing to increasing, or as we'll see, increase to decrease. So the point at which the function changes from increasing to decreasing or decreasing to increasing is what we're going to call that the vertex. But since it's a function of x, we could flip this. Remember our reflections, our transformations. We had two reflections, right? Flip over the horizontal axis or flip over the vertical axis. So you could have a parabola that has been flipped over the horizontal axis. So it could open downward. So you could have a parabola that, maybe looks like this. Maybe a little bit more symmetric looking if I can do a slightly better job of that. It would still have an axis. It would still have a point at which it changes from increase to decrease. Call that the vertex. And then the way we're going to tell the difference between these is we're going to use our transformations, right? So our parent function, as you might recall from earlier, our parent function is going to be y, or f of x, is just simply x squared. And then from there, remember y equals x squared. That was the parabola that looked like this. We call this the squaring function, right? That was the parabola that had its vertex at 0, 0 and opened upward. So the way you would flip it is you would throw a negative number out in front of this whole function. So it turns out it's actually easy to tell whether the graph is going to open up or down. So it's going to open downward. It's going to open downward if that front number, what's called the leading coefficient, so the coefficient on the quadratic term, if that is a negative number. So as we know from our transformations, if that front number is negative, it flips the whole function over the horizontal axis. So that's how we'll know that that's going to open downward. Whereas for this one, if it's never flipped, then that front number, the leading coefficient, will just still be positive. That'll still be a positive number. And then some other things you may have already noticed. For example, if you plug 0 in for x, so if you plug 0 in for x, this term goes away and this term goes away. You just get y equals c. So the y-intercept is always going to be 0, c. Because if you plug 0 in, it makes the quadratic term and the linear term go to 0, and then you get y equals c. So the y-intercept is always 0, c. So for example, over here, if I were to extend this one, a little bit further, it's going to hit again at whatever C is. But keep in mind, these are symmetric about their axis, even though mine's not drawn perfectly. Done correctly, done with some care, this distance here from the axis. So if I were to do this distance to that point, whatever that distance is, if I call that distance 1, then it should be the exact same distance on the other side to get to this point. Those should be the same exact distance. So if you go to the right of the axis to find a point, you should be able to go the same distance to the left to find a point. Because again, if you were to fold this parabola along its axis, it should match up perfectly. So if I go from here to get to that point, let's say we call that distance 2, then I should be able to do the same distance to get to another point over here. All right, so again, these are all things you did in Algebra 2. We're just kind of revisiting it a little quickly. The only parabolas we'll have, though, are ones that open up or down, because those are the only ones that would pass the vertical line test. So if you had a parabola that didn't open upward or didn't open downward, like it's basically the axis of symmetry needs to be vertical. If the axis of symmetry is not vertical, then you don't have a function of x. Okay, so that's another important point here, is the axis is always vertical. That's the only way you're going to get a function of x. Now, there are parabolas that do not have a vertical axis, but they're not functions of x, so therefore not something we're worried about at this moment in time. All right, so there are two forms of a quadratic that we're going to use a lot and find useful. One's called standard form and one's called vertex form. Standard form is the one we've been writing down. So standard form is this one, where you have y by itself, and then the definition for y is on the other side. So ax squared plus bx plus c. That's called standard form. Now there's another form called vertex form that comes from standard form that we can show how one turns into the other, which we'll do here quickly. So let's say you start with standard form. So let's say we take standard form and let's complete the square. So if I take this and complete the square, I factor out a, and then I divide the coefficient of the linear term by 2 and square it. So if I divide that by 2, I get b over 2a, and when I square it, I get b squared over 4a squared. And then I have to keep the equation balanced. So if I distribute the a back in, I have to subtract b squared over 4a to keep everything balanced. Because if I distribute the a, I get ax squared, that's there. I get bx, which is right there. Then I get b squared over 4a minus b squared over 4a is 0 plus c plus c. So these are equivalent functions. I know this one looks a little scary, but it's not. It's equivalent. But I have a perfect square trinomial here. So now I can write this as, let's see, x. And then we want to factor this here. So we need to figure out what multiplies together to get that. So it'd be Let's see, what times itself gives us this. So it'd be b over 2a squared. And then this whole thing is just a constant, so plus c minus b squared over 4a. And then what this gives us is, this gives us what's called vertex form. It looks kind of scary and doesn't look all that helpful, but it is. And what we see here, what we have here is we can use our transformation. So as you can see, if our parent function, if the parent is y equals x squared, well, as you can see, we replaced x squared with x plus b over 2a. In other words, there was a left-right shift. There was a horizontal shift. And then we added c minus b squared over 4a. So there's a vertical shift. There's a vertical shift. And then if a is not 1, we have a vertical stretch compress. So written this way, you can see all the transformations. You can see the horizontal shift right here. You can see the vertical shift right here. And you can see if a is not 1, you can see that there's a vertical stretch compress. So this is actually a very useful form called vertex form. However, it's got a lot of letters, right? You can see the B's and the A's and the C's. So typically vertex form is not written with all the B's and the A's and the C's. It could be. It's just a little intimidating if it is. So instead, typically the way the vertex form, or often the way vertex form is written, is we leave the A, because the A that's here is the same A that's in standard form. So we might as well use it. They're the same number. But instead of plus b over 2a, we typically replace b over 2a with negative h. So we basically let, if we just let b over 2a equal negative h, because that seems weird, like how can we do that? But b over 2a is just a constant. Now we don't know what the constant is. It depends on b and a. So we can replace that constant with any other constant we want. So we're going to replace it with negative h. And then instead of c minus b squared over 4a, we typically let that be k. And this is not the only way to do it. It's just a common way to do it. So vertex form is a times the quantity x minus h squared plus k. H is your left-right shift, and k is your vertical shift, and a is your vertical stretch compress. So this allows you to graph with transformations. So what's important here is that both forms are useful for different reasons. They both let us accomplish things quickly, certain things quickly. For example, vertex form, since all the transformations are apparent to us, vertex form gives me the vertex really quickly, which is why it's called vertex form. So remember, the parent function is y equals x squared. So I'm starting out with a vertex of 0, 0, and then I'm shifting right h up k. So basically the vertex, which is the reason we do, by the way, it's the reason we do minus h, is because then we can think of, we can write down the vertex as positive h, because remember, when you replace x, you have to do the opposite arithmetic, as we discussed back when we did our transformations. So by replacing x with x minus h, we can say that the vertex is h, k, which is why we choose negative h over here, by the way. So the useful thing of vertex form is that the vertex is given to us. Our vertex is just going to be hk. Again, that's just from transformations. That's just simply applying the transformations we talked about earlier. We're starting with y equals x squared, which had a vertex of 0, 0, and then I'm going right h and up k. So my vertex has to be at hk. Again, super useful. I mean, the vertex is arguably one of the most important points on the parabola, if not the most important point, which means that the axis is x equals h. That'll be the axis of symmetry, is that vertical line, x equals h. So those are two things you can get immediately from vertex form. But there's more than that. If A is positive, then we know that our parabola opens upward. If A is negative, we know that our parabola opens downward, so that's very useful. But to get the y-intercept, you'd have to plug in 0 for x and do some arithmetic to get the y-intercept. So for vertex form, getting the y-intercept it's not hard, but it requires a little bit of effort. Whereas like standard form, right away, we know that 0c is the y-intercept. So plug in 0, y equals c is the y-intercept. So we get that immediately. If you want to do the vertex, it's a little bit more work. The vertex, we'll come over here. The vertex is shift left b over 2a. So it's negative b over 2a. And then to get the y value, you have to plug that into the function. So then you'd have to plug that into the function. To get the y value. Or I guess you could, this would be a lot to remember, and I've got plenty to remember. I don't need any more. I guess you could remember that it's just up c minus b squared over 4a. So that's up to you. I personally would just remember that it's negative b over 2a to get the x coordinate, then plug it in to get the y coordinate. And that's my personal preference. But you could remember that it's up c minus b squared over 4a, I suppose. So I guess for those that are clever enough to do it, you could remember that it's going to be that. That means the axis of symmetry is always x equals negative b over 2a. So again, the a being positive is going to tell you that the parabola opens upward, and if the a is negative, it's going to tell you the parabola opens downward. So the standard form has its purposes. It's got lots of purposes, actually. There's more than just this, but like for graphing, it gives you the y-intercept. You can get the axis and the vertex kind of quickly. It requires a little bit of effort. But vertex form, you get the vertex right away, the axis right away, but you don't get the y-intercept quickly. So again, that's why we have two forms that we kind of go back and forth and use. All right, so let's say we wanted to graph a parabola. So we want to graph this quadratic function, and it's in standard form. Well, if it's in standard form, you can definitely leave it in standard form and graph it. That is definitely an option. So let's take a look at that. So this is standard form. We've got g of x is negative 3x squared plus 6x plus 1. So since it's in standard form, I immediately know that a is negative 3. So I immediately know that this parabola is going to open downward. I also know that the y-intercept is 0, 1. Because if I plug in 0, I'm going to get y equals 1. I also know that the axis is going to be x equals negative b over 2 times a. So for this one, it's going to be negative 6 over negative 6, which is 1. So the axis of symmetry is going to be x equals 1. Its vertex is going to be at 1. And again, you could remember the little formula c minus b squared over 4a or whatever it is, but my personal preference is once I know that the x coordinate of the vertex is 1, I would just plug it into the function. Is my personal preference. So the vertex is going to be 1 comma, let's see, that'd be 7 minus 3 is 4. So my vertex is at 1, 4. So my vertex is in quadrant 1, and I'm opening downwards. I'm going to go right 1, up 4, and it's opening downwards. So it's going to have some x-intercepts. So we should probably go find the x-intercepts. So my x-intercepts, let's go get those. So if I plug 0 in, to get my x-intercepts, I'm just going to do the quadratic formula. So negative b squared minus 4ac all over 2a. Let's see what I get for these x-intercepts here real quick. So we're going to get approximately negative 0.15 and 2.15. So we're going to get negative, 0.15 and 0, and then 2.150 for my x-intercept. So that should be enough to graph it. We should be able to do that. Graph it with that. But we also have the following option. Now, you would not need to do both. But the other option is to take a second and go ahead and turn it into vertex form. Now, we'll graph this here in a sec, but what if you wanted to turn it into vertex form? So you could start with standard form and then, as we saw earlier, if you just simply complete the square, so let's take out our negative 3, divide by 2, and square it. That'd be minus 3, so we got to add a 3. So by completing the square real quick, we get a lot of this information pretty, real quick. We're going right 1, up 4, because remember, we're just using our transformations. So my vertex was at 0, 0, but I'm going to go right 1, up 4. So my vertex is 1, 4, just like it was over here, right? Vertex is 1, 4. We just saw that. And I got it pretty quickly over here by completing the square. That makes my axis x equals 1, which we knew already. The only thing that's not obvious is that, not by vertex form, is that the x-intercept is 1. However, we started with standard form to turn it into this. So I have standard form to look at. So 0, 1 is definitely the y-intercept. I've got that by looking at it. And my x-intercepts I've already found earlier. I don't need to find them again. So it's negative 0.15, 0, and then 2.150. So again, we get a lot of that information pretty quickly by turning it into vertex form. So something to keep in mind, just because it's given to you in standard form doesn't mean you can't switch it over to vertex form and graph it that way, because arguably it's just as fast or maybe a little bit faster. We know that A was negative, so we're opening downward. That hasn't changed. So again, I'm not saying you'd ever have to do both of those, but you have the option. You can leave it in standard form and get your information, or you can do vertex form and get your information. Both are going to be valid. So let's go ahead and get this thing graphed. Let's draw a coordinate plane here. Get this thing graphed. So we have a y, we have an x. 1, 2, 3, 4, 5, 6. 2, 3, 4. 1, 2, 3. So let's see. If we go right 1, up 4, there's the vertex. We know we're going to go through 0, 1, so here's our axis. We know that 0, 1's on there, which means we have to have one at 2, 1, because axis of symmetry. And then we know we're going to go through negative 0.150 and 2.150. So it's going to just miss the origin and just miss 2. So if we draw the parabola in there, it's going to look like that. It's a relatively narrow parabola because it got stretched vertically by 3. So it's, narrow compared to the parent, right? Remember what the parent function looks like. The parent function is at 0, 0, 1, 1, 2, 4. So the parent function looks like this. This is our parent function right here. So the blue one is a little bit more narrow because it got stretched vertically by 3. It's been flipped over the horizontal axis. Got shifted right 1. So it's had some transformations applied to it where like this is a rough sketch of our parent function, y equals x squared. Similar shape, but it's been transformed. Now, for this next example, it's already in vertex form. It's already in vertex form. So we might as well leave it that way, right? So A is a half, so we know that it opens upward. We know that the axis of symmetry is going to be left 3, right? So it's going to be x equals -3. And then my vertex, you're going left 3 down 2, so it's left 3 down 2. So real quick, you get opens up, axis of symmetry, we get its vertex. The only thing that's not really obvious is the x and y intercepts. So if you're going to leave it in vertex form, you're going to have to do a little bit of work. So like if you plug in 0 for x, not that this arithmetic is difficult, but still a little bit of work. You're going to get 9 halves minus 2. So 9, it's 4.5 minus 2 is 2.5. So you're going to get 5 halves. So we're going to get 0, 5 halves for the y-intercept. And then if you want your x-intercepts, you're going to plug 0 in for y. Then you got to solve this for x. So we're going to do that quickly here. No need to do the quadratic formula. You just simply solve this equation real quick. So square root both sides, you're going to get 2 equals absolute value of x plus 3. So we get x plus 3 equals 2. So x is -1. Or you get x plus 3 is -2. So x is -5. So our vertex was in quadrant 3 opening up. So we definitely hit the x-axis. And we're going to hit it at -1 and -5. So we're going to hit it at -1, 0 and -5, 0. So again, we got lots to graph it with here. So let's go ahead and draw a coordinate plane, get this thing graphed real quick. So let's see, our vertex is at -3, -2. And then it goes through 2.5 on the y-axis. It goes through -1 and it goes through -5, 2, 3, 4, 5. And then our axis is right here. So we know that we're going to have another point. Let's see, this is 1, 2, 3 to the right, 1, 2, 3 to the left, right there, using our symmetry. So here's our parabola right there. So notice though that the way the nature of the parabola, it always increases somewhere and it always decreases somewhere, and the vertex is where that changes. So for example, this one decreases. So this one is decreasing on the interval -infinity up to -3, and then it's increasing on the interval 3 to infinity. And if you prefer the definition for increasing decrease that that allows for the endpoints. 3 is in the domain, so you're allowed to put a bracket. Either one, I'm not going to complain either way. But it changes from decrease to increase at -3. That's what's important here. So the other thing that we want to point out is that parabolas always have an absolute max or an absolute min. They got one or the other. So if you look at this one has an absolute min. And this one up here had an absolute max. So we talked about how functions can have relative max and min values and absolute max and min, and parabolas always have an absolute max or min, and relative. It's technically both, right? That's a relative max, and this is a relative min. But parabolas will always have that. So this thing, for example, so for this last one we did, we have a relative and absolute minimum value of -2 at x equals -3, right? So that is a relative. This is a relative min, but it's also an absolute min. So the smallest y value possible for that function. So every quadratic function has an absolute min or an absolute max. It's got one or the other. And the way you can tell is by looking at its direction of opening. So if the parabola has a positive a and it opens up, it's going to have an absolute min. We just graphed two quadratic functions. We don't, and I talked about how to change this over to vertex form earlier, so we don't need to go through this one again. But this next example talks about the the absolute min, absolute max that I just discussed, where as soon as you identify it as a quadratic function, like when I look at this, I see x squared minus 4x minus 5, that's a quadratic function. Well, since a is +1 and it opens upward, right, my parabola opens upward, I know I have an absolute min. So this has an absolute min. Now, the question is, how do we go find it? Well, you just need the vertex. All you need is the vertex. So this is in standard form. So since it's in standard form, the axis is going to be x equals -b, or the opposite of b, over 2a. So that'd be 4 over 2, which is 2. So that makes the vertex 2, comma. Again, I prefer to just plug in the x to get the y. So it'd be 2 squared minus 4 times 2 minus 5. So it'd be what? 4 minus 8, -4, -9 maybe. So my vertex is at 2, -9. So there's an absolute minimum value of -9 at x equals 2. So I now know that the lowest or smallest y value for that quadratic function is -9. There is no smaller output for that function. Whereas one like this, right here where a is -1, right? So we have f of x is -x minus 6 squared plus 12. So a is -1. This thing's going to open downward. So we have an absolute max. But again, how do you go find it? Well, it's in vertex form, so that's pretty handy. So the vertex is, you go what, right 6 up 12. So there we go. That's all the information I would need. This thing has an absolute maximum value of 12 at x equals 6. So I know that for the input of 6, it gets its max y value of 12. Every other output would be smaller than 12 because it opens downward, and that's the vertex. So again, just finding the vertex will give you that absolute max or min for any quadratic. So vertex form, one of the other uses of vertex form, one of its, arguably its most important use is it allows you to write the equation for a parabola relatively easily, especially if you know the vertex. Otherwise, it's a little bit more complicated. But let's assume that we actually know the vertex. Well, if I know the vertex, so if I know the vertex is at -5, -8, well, then I know my function. Remember, vertex form looks like this, where hk is the vertex. So yeah, I don't know what a is, but I know that h is -5, so I went left 5, down 8. So by just knowing the vertex, I know everything I need to know about the quadratic function except for a. But that's no big deal. I can go find a. They tell me that the parabola contains another point, 1, 2. So let's go find a. So let's go find the a value. So this is just a coordinate, x, y, that is on the graph of the parabola, therefore solves this equation. So I can plug in 2 for y. I can plug in 1 for x. And then I get 2 equals, 5, 6, 4, 36, a minus 8. So I'm going to get 10. So a must be 10/36. Oh man, that'd be what, 5/18, if I did that right? So it should be 5/18. So this would be the equation for that parabola. We can check it and make sure that 1, 2 is actually a point on that graph. So let's check it. If I plug in 1, I get 36 divided by 18 is 2. 2 times 5 is 10. 10 minus 8 is 2. Yeah, that works. So that presumes, though, that we know what the vertex is. If you don't know the vertex, well, that gets a little bit more complicated. Not something we're going to take a look at right now. It involves solving a system. It's interesting, don't get me wrong, but it'd make this video a lot longer than it already is. So presuming you know the vertex and one more point on the parabola, you can come up with the equation for the parabola, relatively easily. All right, so let's finish this off by looking at one situation, another situation from economics, where a quadratic model would make sense. So suppose a particular calculator company determines that the number of calculators it sells is modeled by this equation. So we get x equals 21,000 minus 150p, where x is number of calculators sold, and p is the price per calculator. So they've done some research, and they've decided that depending on what the price is, they can determine the number of calculators they will sell based off that linear function here, this linear equation. It says write a function that would model the company's revenue. Ooh, we want to model the revenue. So you got to know what revenue is. So revenue, in case you're not familiar, revenue is where you take the price per unit times number of units sold. So for example, let's say you've got 50 candy bars and you sell each candy bar for $2, right? So you got those fundraiser candy bars, those big giant candy bars, right? In that box, a huge candy bar, and you charge them $2. So let's say you got 50 of those and you charge them $2. So if you sell all 50 at $2 each, you have a revenue of $100. That's your revenue. That's not your profit. It's your revenue. Profit is how much you make after all your costs, right? You had to spend some money to make some money. So that's another thing. But revenue is just price per unit times number sold. So let's see if we can't do that. Let's do this. Write a function that would model the company's revenue, find the price that would maximize revenue, and then find the maximum revenue. All right. Let's see if we can't make this happen. So I'm going to let's let revenue be capital R. Let's let revenue be capital R. So price per unit, that's P, times numbers sold, that's X, right? Well, right now, R would equal PX. That's 3 variables. Ugh, I don't want to do anything with 3 variables. Let's see if we can get that down to 2 variables. Well, I know what X equals, so I could write revenue as simply a function of X. Oh, I'm sorry, not as a function of X, because we know that you'll see why here in a sec. It's going to be P times, well, X is 21,000 minus 150P. So revenue is actually going to depend on price. So it's going to be a function of price. So if I distribute that P, I get negative 150P squared plus 21,000P. Ooh, that's a quadratic function. Plus 0, right? That's my C value, plus 0, which makes sense, right? If you charge nothing for the calculator, your revenue is nothing. So if P equals 0, then your revenue is 0. I mean, if you don't charge something for it, and I can get any money, no revenue. So I get this quadratic function that opens downward. Look at that. So A is negative 150, so this parabola would open downwards. So it says find the price that would maximize the revenue. So I want to maximize this function. I want to find the vertex. I want to find this point right here. I want to find that vertex. So I don't need to graph this. I don't want to graph it. But if I did graph it, this would be revenue, this would be price, and this graph would look something like this, right? It's got to. So I want the max revenue. I want this number right here. I want that. I want to know what that is. And I'm going to get that from finding the vertex. So the axis of symmetry is going to be x equals negative b all over 2a. So negative 21,000 over 2 times negative 150. So we get 70, except for it's not x. I apologize. We're not. That's p. I'm sorry. That's p. It's p, right? See, it's right here. P. I can see it. I don't know why I didn't write it. It's just because we're used to it being an x. It's a p. So my vertex is going to be at 70. So we know this point is 70. And then we need the rest of it. So if I plug 70 in to get that revenue, it's going to be negative 150 times 70 squared, 21,000 times 70. So that max revenue is going to be, let's see, $735,000. So there's a maximum revenue of $735,000 if the price per calculator, right? I think we're doing calculator. So the price per calculator is $70. Now, you might be thinking, wow, so that's their max profit? No. Profit's different. This is max revenue. So they could maximize the revenue at $735,000. But if you study econ and get into the weeds a little bit with this, you don't always want to maximize revenue. That might not maximize your profit. But that's not our concern right now. We were just showing how one example of how quadratic functions can be used to model something, some real world quantities.